So we have something called as the radius of gyration. So let me put it this way. Say I have a mass, a disk, or any shape and size, doesn't matter. So it has a particular moment of inertia. You guys agree? So I have an object. Let me start the discussion this way. Say I have an object and it's rotating along, say, this axis. And the mass of this object is, say, it can be anything actually. Mass is, say, theta. No, let not take theta. M itself. Now, I do some work and it is rotating at a particular velocity. It's rotating with a particular velocity. Now, if I want to create a same effect by replacing this entire object with a single object, but here too the mass is the same. Here too the mass is the same value. But the moment of inertia, that is the resistance to the rotation, whatever this gave, the same amount of resistance this also gives. And this length from A to B is your radius of gyration and stuff. Okay. So that length AB is your radius of gyration. So let me read through. The basic idea here is, say you want to rotate an object and now want to replicate that effort. We are replicating the effort. So what we can do is, first we can start with considering a point object which has the same mass as the original object. So mass will not change. Second thing is, we need to place at a certain distance from the same axis of rotation so that the moment of inertia is the same. This distance is known as radius of gyration. Okay, this distance is your radius of gyration. So let me put it across to you guys in this way. All of that was a bit confusing. So let me put it to you guys in. Oh, it's already running. So can you see that both are rotating at different rates and stuff? On the left, you have a disk. On the right, you have a point object. Now, can you see the mass? Are they same? Yes. But you can see clearly that the amount of the rate at which the objects are rotating, it's altogether different. What I can do is, I can change the radius. Say example, I change it to 1.24 of the second point object. I'm not changing anything on the left, only on the right. And let's see now what happens. You have a slower rotation. On the right, we have a slower rotation, so that's not working out. So with some calculation, I found out the value is around 0.85. Somewhere in between this, but yeah, let me go with 0.86. So now let me reset both and let's see what happens. Can you see that? Both are almost rotating at the same rate. Because their moment of inertia, can see that I value over here, it might be a bit too small for you guys. Here on the left it is 2.16. Here on the right it is 2.2. So of course there's quite a bit of difference with decimal places. But point is, I'm close. How did I change? Did I change the mass? I didn't change the mass. What did I change? I changed where the object is rotating, at what distance the object is rotating. The point object, what distance it is rotating. Remember, the point object mass has to be same as that of the entire, whatever the object is on the left hand side. That is not changing. What I can do is, I can change where, at what distance it rotates. The point object, at what distance it rotates. That I can change, and that is your value. What value? That is your radius of gyration. That distance from the center to the point object, that is your radius. Okay. So now radius of gyration of a body with respect to its axis of rotation can be described as the distance from the axis of rotation to a point where the body's entire mass could be concentrated, resulting in the same moment of inertia around the given axis as with the body's actual mass distribution. All that fancy words, it means whatever I just told now. So let's look at a bit of math and then finally look at the factors and stuff. Okay, so to derive this, I can consider this object to be made up of n number of masses, all with same small unit of mass. So uniformly distributed object, say of length r1, r2, r3. Okay, so basically I have an object consisting of n particle situated at r1, r2 and r3 and so on and so forth. So let's consider, or suppose, a rigid body consists of n particles of mass m each, situated at distance of r1, r2, r3 dot 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 rn from axis of rotation. We can call this as PQ. PQ. Okay. Now, your moment of inertia of such an object about PQ would be, about the axis PQ would be I is equal to mr1 square plus mr2 square plus dot 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 mrn square. So what is common? M is common. What is left out? R1 square plus dot 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 Rn square. Okay. So now I'm going to multiply and divide with n. I'll explain why. So R1 square plus dot 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 Rn square. Now we know that we have m particles and there are n of it. So m times n will give us capital M. What is this capital M? Yes, total of what? Total mass of the body. So I can replace this entire thing with capital M and this with R1 square plus dot 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 Rn square. This entire thing divided with n. Now, if k is the radius of gyration, guys. So if that is our radius of gyration about the axis PQ, then I will be equal to mk square. So basically this is m. I'm calling this as m. And that's k. Right? So from 1 n to what can I tell? What is the k value? Therefore, from 1 and 2, what we have is k is equal to root of r1 square plus dot 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 rn square, this entire thing divided with n root. So that's your k value. That's how you'll be able to figure out the k value. Right, finally I have a bit of small conclusion. So factor that affects your radius is shape and size of the body, position and configuration of axis of rotation, distribution of mass within the body. So basically it's commonsensical. So if I happen to have the radius of the axis of rotation somewhere else, then the distribution and the structure changes, right? So we have seen all of this. And your moment of inertia will be different. Okay, just by changing this. So how the object rotates. So you can see actually the left object is also rotating, just that we are not able to see the difference. Okay, I'll be able to do this. Yeah, that's better. So when the moment of inertia gets affected with just by changing the axis, obviously even the radius will also get affected with change of axis. So the same set of factors will affect. Okay, so same set of factors will affect, and yeah, we end up with all this as your factors. Okay, so quite simple concept. So you can pause, have a look. And derivation is also quite simple.